Okay, we look at the pressure difference, and the unit is Pascal. So this is a ballistic distribution, and this distribution is analytical solutions for laminar flow inside the tubes, right? So we have delta P will be the pressure drop, because when the fluid flow inside the pipe, we have a large energy here, and because of the friction, and energy is lost to maintain the same amount of velocity along the pipe, and at section 2 some of energy will be lost to do the work, right? So we're going to see some loss of flow work that represent by this delta P pressure difference, right? That will you just include just right there 2 Pascal, and then you know about the diameter of pipe, make sure this in meters, and then we have the length, which is 2 meters, and then we have the dynamic viscosity, right? So we have a dynamic viscosity. And before we go to describe the pressure differences, I think it's better for me to look at the property of materials. So mu is the dynamic viscosity. So the unit of dynamic viscosity is a Pascal second. And this dynamic viscosity varies with the fluid, right? So in this case, we are looking at the water. So we have to find the dynamic viscosity of the water, right, to solve this problem. This velocity actually is a local values, a point, right, in space. So in order for you to calculate the mass flow rate, we have to integrate over a cross section, right? So in this case, the cross section is being written in the form of radius. So we have a point there, a very small what you call it, a thin layers, a strip, right, along the radius location, and then we integrate it for 300 degree or in 2 pi, so that this will give you the cross section on plane. And then we have the local density, and then the density of the water, right? um, and then we can have we have this mass flow rate on the pipe, right? Now we want to look at the different you can see that this equation is different from what you have learned in the first video clip, right? So that the earlier mass flow rate is based on local velocity. Now I'll give you an equation here that represent by the average values, right? So this one is based on average values, and this one based on local velocity. Right. So we can see here that we can find the average velocity. These are values that we have earlier, right? And this value is placed here. Oh, right, over there, and then we divide by the area for the pipe, because when I say pipe, the pipe means circular cross section, and then we have the density, the average density of the uh, water, right? So in the first lecture, uh, the um, when we evaluate these values, this give you the average density of the uh, fluid. So that will be your quiz. I also show you the step to doing it. But what you need to do is just put in the values, right? And then calculate the um, volume flow rate and mass flow rate. So any question? Now let's see if I can go for what it mean by pressure drop. So I have another minute there. So this is a experimental arrangement, right? This one for gas phase is the experiment to measure the pressure drop. This one is water phase for liquid phase, and you can see the differences. So we have a pressure orifice at this location. So this is a pressure orifice, and the one there. Right, I'm going to finish this one. So I'm going to continue the lectures afterwards, right? The next lecture. So that pressure orifice, and we connected to instrumentation called manometers and piezometers, right? Mm, so these are manometers, and this is a piezometer, and the height we call piezo head, right? So this one we have a pressure difference given by H, and piezometer is also given by the height of the water column. So it will finish in 45 seconds, and then I'm going to end my lecture here. Thank you very much for the cooperation that you have given to me. Um, and hopefully in the futures this class will run smoothly, and I will give you time to ask questions, inshallah, right? um, right, so I think I'm going to end my lecture today. Assalamualaikum.